well known. It's a famous result of Lovász that the chromatic number of this graph is n-2k plus 2, and well, you can characterize the fractional chromatic number in terms of homomorphisms into this graph. So it's a rather central object in some areas of combinatorics. And a slightly less well-known graph is its induced subgraph, which is called the Schreiber graph. Maybe I'm pronouncing it good, I'm not sure about that. So the Schreiber graph is an induced subgraph of the Kneser graph, and you get it as follows. You fix a Hamiltonian cycle on the vertices of the ground set, and only those vertices will belong to the Schreiber graph, which correspond to subsets which are independent in this fixed Hamiltonian cycle. So somehow a cycle governs which sets you throw away, and the rest is just like as the Kneser graph, disjointness means connective image. And well, these graphs are studied with the topological method, and often questions, so often their chromatic number is very interesting. For example, the Schreiber graph is interesting because it has the same chromatic number as the Kneser graph. I'm not proving it right now, but it's considerably smaller than the Kneser graph. But it's color critical, which means that if you drop a single vertex from the Schreiber graph, its chromatic number will decrease. So in some sense, the Schreiber graph is one of the reasons why the chromatic number of the Kneser graph is so high. And well, Gabor Simonyi, who is my advisor, and Rona Baroni are doing some topological combinatorics, and they became interested in the question that how many vertex-disjoint Schreibers are in the Kneser. This sounds rather specific, but we will reformulate it in terms of Hamiltonian cycles and independent sets in a minute. But first, let me mention that if you just drop the disjointness condition, so how many Schreibers are in a Kneser, well, in all the interesting cases, it's just the number of Hamiltonian cycles on a ground set of size n. So if you drop disjointness, in all the interesting cases, it's trivial. It's n-1 factorial over 2.
Sorry, I'm lost about the definition of the Schreiber graph. So,
yeah.
Could you show me an example, please, for?
It's a rather large graph. I mean, both the Kneser and both the Schreibers are rather large.
If
it's in the graph, in Kn, nothing. Hamilton cycle has nothing to do with the Kneser graph. Just n cycle.
So 1, 2, 3.
Oh,
and so the k-subsets of these are the vertices of the Kneser, and only those k-subsets we consider in the Schreiber case, which are also independent in this cycle, which is
okay. So k independent sets. Okay.
Alright, at first it's rather weird, but these objects are interesting because of their chromatic properties. Alright, so let's reformulate it so that it's, well, it's easier a bit. So suppose that you have two Schreiber graphs which are vertex disjoint. This means that they correspond to two Hamiltonian cycles, and the two Hamiltonian cycles do not share an independent set of size k. In other words, they are on the same ground set. Their union has independence number at most k, smaller than k actually. So let us introduce the function fnk, the maximum number of Hamiltonian cycles, so we want many Hamiltonian cycles, and our restriction is that the union of any two cannot contain two large independent sets. In this language, fnk-1, well, the definition is off by 1, fnk-1 is just the maximum number of vertex-disjoint Schreiber graphs.
Is it k or k-1? Alpha. Is it k or k-1?
You said
well,
smaller, but all incorrectly.
I don't know which one. I thought it was k-1.
Yeah, here, so the maximum number of vertex-disjoint Schreiber subgraphs in KGN is exactly k-1, yes. but I just defined, when I define f, I'm just defining for f and k. So the definition is v.
Quite confusing, thank you.
I'm sorry about that. I can promise it will not be ever more confusing. So let's keep the definition. And well, we will see in a minute that in all the interesting cases, k is a linear function of n. So instead of f and k, we will study f and constant times n. And well, one of the best motivation for myself to study this function was the following observation. I'm writing here theorem, but it should be called an observation. But we observed it with Rona Haroni, that for f and c times n, there's a critical value of c, or a threshold for c, and where something interesting happens. So the SF function behaves as follows. At the threshold value, we have no idea what does it do, but when we choose c smaller than the threshold, what does it mean I choose the c smaller than the threshold? This means I exclude even smaller independent sets, so I'm more restrictive, and it turns out that the function becomes bounded independently of n. On the other hand, if I increase c from the threshold, which means I'm allowing slightly larger independent sets, well, to be perfectly honest, I'm allowing a constant times n more independent sets, so yes, that should be mentioned. Then the answer is immediately exponential in n.
Isn't everything in 0, 1/2?
Yes, moreover in a quarter, 1/2, yes.
Exactly.
Yes.
So why do we have 0, 1?
Uh,
Simply 0, 1.
So that no other people would ask why is that a quarter and a half.
Because that's his
But I will tell you that.
natural habitat.
Oh, I see. But now you spoil the next slide. I mean, part of it. Alright, so, well, first of all, we do not know what happens at the threshold, but what's a slightly more annoying thing that we do not know where the threshold is. So, this is actually, so this should be called an observation because this is very easy to prove. I mean, I probably shouldn't even call it the probabilistic method. You just do stuff randomly and so you just use a single randomness and so this is very easy. I will not prove it, but please believe me that the proof is very easy. Alright, so keep the theorem that serves as a motivation, and well, we couldn't manage to prove or to find the threshold, but we have no trivial lower and upper bounds. So let me tell you something about them. Let me tell you the trivial lower and upper bounds that were already spoiled. So there's no point of choosing c larger than 1/2 because there are already no independent sets larger than n/2 in a Hamiltonian cycle. So obviously they won't be in the union of two Hamiltonian cycles. So if c is larger than 1/2, we can take all of them. If c is smaller than 1/4, then again the problem is very easy, well, not interesting. By the following reasoning, suppose that you have two Hamiltonian cycles, you take their union, and well, you can use, in all interesting cases, you can use Brooks' theorem, because the maximum degree is at most 4 in all cases, it's connected in all cases, and it's not a complete graph in all the interesting cases. So it's colorable by 4 colors. So the largest color class is an independent set of quarter times n, which means if you forbid those, then you can have only a single Hamiltonian cycle. So that's the trivial region. And well, the upper bound is rather easy to improve. For example, I mean, probably some of you had the first idea to just take stuff randomly, and well, uniformly random constructions immediately improve it by, well, considerable amount. And well, not so uniformly random constructions improve it even further, but these are still random constructions. Well, maybe I shouldn't say these are random blow-ups of some fixed constructions. But whatever. The main point is that the upper bound is still rather easy and nothing interesting happened yet. And this is the best upper bound that we could get. But I have a feeling that we are really far from the truth in terms of the upper bound.
Random blowout?
So you have a construction, say, on ground, and you take copies of this ground set, and you take copies of the construction, and from each one you choose a cycle randomly, and you repair them to be a Hamiltonian cycle in the whole thing, and the size of the independent set will not increase that much. And well, if you have, so there will be a small error, but the error is small, and this way you get an exponential amount. So it's really, really easy actually. On the other hand, we could improve the lower bound, which was a surprise for me. I will explain it in a few minutes. And now the proportions on this picture are right. So it's a rather modest improvement. Instead of 0.25, it's 0.26. But actually, this is the part where we really learn something about the behavior of this f function. So this is the part where I feel that I learned something. I discovered some interesting effect. Well, the proof is not at all easy, and it uses another theorem which has really similar, not really good to read proof. But let me say a few words about the place where it's exactly a quarter. So there already something non-trivial happens, and I would like to say a few words about it. So what's the value of f when c is exactly a quarter? So recall the Brooks reasoning. If c is smaller than a quarter, it's not interesting. The value is just 1. Right? So if c is exactly a quarter, you can have 2 by this picture. So one of the Hamiltonian cycles is the one with the bold edges, which goes like u, 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 and the other goes like e, e, e. And well, you just wrap around them at the end. And well, as you can see, their union is covered by disjoint K4s, so there is no room for an independent set of size quarter or larger than a quarter. Of course, there is one with a quarter. So we see that sometimes f can be at least 2. And to be honest, my gut feeling was that so when I first heard about this, I didn't really know the threshold. I just know the trivial bounds, and we were just trying to prove something around the trivial bounds. And my gut feeling was that this is not an interesting problem. I mean, the Schreiber graph is a lot smaller than the Kneser. I mean, for this weird Brooks reasoning, it seems like at a certain range, the problem is not interesting. But my gut feeling was that but at the first instant, when you have room for 2 of them, then it will blow up to an exponential amount. But it doesn't do that. And now I can say a few words about why it doesn't do this. So, from the Brooks reasoning, we didn't really use the full power of the Brooks theorem. We used something like this. This is not Brooks. This is not true at all because we need connectiveness, but that's not bother with these things. So if delta is at most 4 and we 4 with k5s, then then we have a lower bound on the independence number. And there are many similar theorems like that with, well, for example, this is what we use. Lakendu says that if delta is at most 4, so that's the same, but we now forbid even k4s, not just k5s, then we have a slightly better lower bound on the independence number. I mean, one would expect such a thing to be true, and they worked really hard to prove it. So it's not an easy theorem, but still, so it feels better to use it because of that. And well, using this, we can have a very nice lemma, but I can't talk enough for you to give the feeling of the niceness of this lemma. So I really skip the lemma, and I just I want to say that using this theorem and some 10 plus pages of work, so really one has to work for that, one can prove that if we have a graph that's a union of two Hamiltonian cycles and the independence number is at most a quarter times n, then the union of these two Hamiltonians, so the graph must be covered by disjoint K4s. So in a very specific sense, it must look like that. I mean, you might connect them in a different way, but it must be covered by disjoint K4s. And that's the statement for which you must, well, for which I had to, or we had to work a lot. And after it, it's rather easy to show that if n is large enough, you can't have only two of such cycles. And for 8 and 4, some miracle happens and the ground set is too small, so you can have 3. But otherwise, you can only have at most 2, and they must look like something like this. And otherwise, you can't have just 1. And well, even the fact that this Fn and a quarter times n is bounded, even that I cannot prove without using this theorem, which is a rather uncomfortable proof. So I suspected that it's trivial, but I couldn't do it in a trivial way. So that was the first problem that I would like to talk about. Are there any questions about this? I mean, there were any questions, so it's no surprise if there are not more. Anyway, you can ask them at the end if there are more. So, the next problem. So this problem was essentially open because the interesting questions are not solved. The next problem is already solved. So I would like to talk a bit more around it because, well, I enjoy open problems if I'm in the audience. So I assume that you do too. So I am talking more about open problems and less about things that are not open anymore. So the motivation for the next problem is. Well, it comes from the Shannon capacity. Janos Körner and many co-authors has had a desire to somehow understand Shannon capacity, but they went a long way. They generalized it, and then they looked at the special case of that generalization and the special case of that. So they arrived at a really distant cousin of Shannon capacity, which is the following problem. It's called colliding permutations. So we say that two permutations are colliding if there's a coordinate where their difference is plus minus 1. So, for example, these two permutations are colliding because here at the first coordinate the difference is 1, and well, we don't care about the others, but of course here is the difference is 1, here is 0, 0, but even a single coordinate where the difference is 1 is enough for two permutations to be colliding. And for example, these are not colliding because the difference is never plus minus 1, so it's 2, 0, 2, 0. And Körner and Mavenuto asked, what is the maximum number of pairwise colliding permutations? They asked it in a little bit more specific manner. They conjecture that this maximum is just the middle binomial coefficient. Oops. So the maximum number of pairwise colliding permutations, they conjecture, and it's, so I would also conjecture that it's the middle binomial coefficient. And it's a really cute conjecture, and it's slightly unusual because here the upper bound is trivial and nobody knows the construction, but up to n equals 12 we have constructions, obviously by computers, and one can look at these constructions for a few hours. I did it myself, but couldn't come up with anything clever. So the upper bound is trivial by the following observation. If you're looking at a coordinate, you can only have a collision if you see numbers with different parity. I mean, an even number can't collide with an even number because the difference is divisible by 2. So the maximal possible number of pairwise colliding permutations is the maximal possible number of so-called parity patterns of a permutation. I mean, you have to choose the position of the even numbers, and if you choose it for two permutations with the same places, those cannot collide. All right, and well, this seems to be a very, very distant cousin of Shannon capacity problems, which I'm not defining, but let's just say they are hard. But so this I will just tell you this. I will not really show you that this is not so distant of a cousin. So we can think of colliding permutations. So this problem as follows. This graph is governing what collides with what. So one can collide with, so neighboring numbers can collide. So if you are looking at the coordinate, there is a collision if they are neighboring numbers. So this graph governs colliding. If we change this graph slightly, this is a matching. So, in other words, the collision of 2 and 3 doesn't count. The collision of 4 and 5 doesn't count. So it's harder to collide. It's a completely different problem with a probably completely different solution. But this is sometimes called matching colliding problem. This is actually a Shannon capacity problem in disguise. So this problem about permutations and maximal size of compatible pairs is actually a problem of determining the Shannon capacity of this family of graphs, which is well, this was rather surprising for me. So this shows, well, that shows that it's not. So these problems are not so distant cousins of Shannon capacity problems. But these were still rather hard. So we looked for even easier problems. How much time do I have?
You have 16 minutes.
16, usually. Much. All right. And so there is a very natural correspondence between permutations and Hamiltonian paths. And well, if you're interested in problems where you are so if you're interested in problems where you are looking for the maximum number of pairwise compatible permutations, some of them could be reformulated to the maximum number of pairwise compatible Hamiltonian paths. And since I myself like graphs a lot better, I was more interested in these kind of problems. So let me show you one very easy archetype, very easy type of this problem. So the maximum number of Hamiltonian paths where we require an odd cycle in each union. What is this number? It's very easy. You prove it in less than a minute. It's the number of balanced bipartition of n, which is well, the middle binomial coefficient, roughly the middle binomial coefficient. So why is this true? So we need many Hamiltonian paths, and in each union we need an odd cycle. Well, having an odd cycle means not being bipartite, right? So Hamiltonian paths is a balanced bipartite graph. So if you already chosen a Hamiltonian path, you cannot choose any more of them with the same balanced bipartition. So the number of balanced bipartitions is a natural upper bound. And it's also a really easy observation that if for every one of those bipartitions you choose one, there will be so no union will be bipartite. So this is rather easy. And let me introduce a notation for these three lines. So by Hn odd cycle, I would like to, so Hn would be the maximum number of Hamiltonian paths on a vertex set of size n, or on n vertices, where each union contains what I write here, an odd cycle, which is, well, this, but this is just a shorter notation for the middle binomial coefficient, and sometimes it's divided by 2. So let me show you some other results of this type. And the second problem in the title is supposed to be another result of this type. So these results are from various subsets of Cohen, Facchini, Körner, Monti, Mesciutti, and Simonyi. And, well, first of all, let me just restate what was on the previous slide. Right? So for odd cycles, this function is roughly 2 to the n. And for triangles, it was roughly between 2 to the n and some other thing. Observe that if we write any specific non-bipartite graph here, the upper bound of 2 to the n still applies because any non-bipartite graph must have an odd cycle, so it's a relaxation of the problem if we only require some odd cycle. So for K4s, for example, for K4s we have a better upper bound. And these numbers are not really important, but it's important that for these things the answer is something exponential. This will be improved in the next slide. But there is another interesting phenomenon. It happens when you ask the same question for even cycles. It seems that asking for an even cycle is barely a restriction at all. And asking for an odd cycle reduces the answer down to exponential, but asking for an even cycle only reduces it by a polynomial. We can almost take every single Hamiltonian path, which is, well, it was rather surprising for me, but it seems like this is the truth. And
So again, each and even cycle is what in words?
is the maximum number of Hamiltonian paths, where each pairwise union of them must contain an even cycle. So this is what I would like.
It's very difficult for a fairly rich graph to have only odd cycles. It's exactly the same as it has only odd, the negation of it has only odd cycles. But it's very hard to have only odd cycles in a rich graph. Just about impossible.
Well, I didn't have this intuition, but now I do.
Yeah.
That means that it has linear number of actually very small.
Yeah, it's instant.
All right. Of course, I see why. Oh, okay. All right. Nevertheless, I was surprised at first.
Yeah. It is surprising because it looks the same.
Yeah, it is really close to the maximum number. Yes. Okay, and well, it is also very, well, not very interesting. It's very interesting, but it will be more interesting in the next slide, when you know what's on the next slide. So, that for C4s, the order of magnitude drops. So we do not know the answer for even cycle, we do not know the answer for C4s, but we know that for C4s, it must be less than for the even cycles. So C4s and even cycles are very different here. And it will turn out in the next slide that odd cycles and K4s will be exactly the same. So the next slide we will, well, I will say a few words. I will not really say a few words about the proof. I will say nothing about the proof, but I will tell you that H and odd cycle is equal to H and K3. So in the odd case, these two things are equal, but in the even case, they are very much different. And well, the last result is just K14, and the answer is again more than exponential. So what's another interesting phenomenon, that for every bipartite condition, the answer is more than exponential. And well, we already saw that for every non-bipartite thing, it will always be just exponential. That's easy. So it would be a natural question whether it's true that for every bipartite we will get more than exponential. The answer is not known yet, but we are fairly convinced that it's false. So we are fairly convinced that there should be a bipartite graph with only an exponential answer, but it's not so easy to find.
Say it again.
So we are fairly convinced that there should be a bipartite graph, which with the property that I ask for Hn and this bipartite graph of mine, and get an exponential growth. Not like that, but so much smaller. So right now, all the graphs which are bipartite, we have constructions of size more than exponential. So it's still open whether it's more for all bipartite graphs, but we would be
one particular bipartite graph, which if you forbid it,
then the answer drops to exponential. Yes. But
By the way, what do you know about the cube?
3-dimensional, 4-dimensional.
I'm just asking
Nothing.
because that's richer than
No, it's-
C4.
but for 4-dimensional, it's impossible because the degrees are too large.
Bármelyeket meg kell tartalmazni, ez egy erősen.
But in the union of two Hamiltonian cycles, you can't have a 4-dimensional cube. I mean, not in every interesting case. The degrees are 4 there, so it would be disconnected. So those are 16 vertices where all the degrees are full, so it can't be connected to the rest of the graph. But I have no idea what happens at the cube. It's interesting. I don't know.
but wait, but there the bounds are much bigger than for C4.
Excuse me again?
But then the bounds are much bigger than for C4. If we forbid a C4, if there is no C4,
Here we require a C4. So for the cube, the bounds are, well, should be smaller than, because we require more. Yeah, it should be smaller, but we still have no idea what happens. It's an interesting question.
get it.
All right, so let's move on. So a few results presented, and well, the contribution of István Kovács and myself to the subject is that requiring an odd cycle and requiring a triangle is exactly the same. Well, it produces the exact same outcome. And how much time do I have left?
6 minutes.
Oh, still. All right. So the upper bound still holds because if you require a triangle, then you can't have more than the odd cycle. So the whole thing's. So for the whole thing, you just have to construct, and it's surprisingly hard to construct. I mean, we're done in 1 minute because I do not plan to talk about this for a long time. So it's a very easy observation that it's enough to prove for the odd case, because well, for the even case you need the same number of Hamiltonian paths, and if you have a nice construction for an odd number, for an even number you just add another vertex and finish those cycles which are already compatible. So this should say that it's enough to prove for odd values, and for odd values this is the required amount. And well, it turns out that instead of this amount we construct this much Hamiltonian paths. So well, this says something about the construction. This is not really a construction of the type that here's the magic definition, and by some clever argument I can show you that any two defined in this magic way are compatible, but it's much more tedious and it takes more than 10 pages, so it's rather nice to have it and not have to work for it anymore. Alright, so that's all then. Thank you for your attention.
There were some questions, but maybe even more.
What happens? Take your bipartite graph that you want to forbid.
You want to require it.
I want to require. Okay, either it kills everything because there is no way of having even two Hamilton paths, which is trivially done. Ask whatever, ask any four regular graph.
Of course, any four regular graph doesn't produce an interesting.
So that's out. So take one which is in the intersection of two. Take two of these Hamilton paths, they intersect in this one. And now keep the way they are there and use the rest of the graph, the n minus whatever, 25 vertices, to get your Hamilton paths. Done.
What? So why can't I have more than exponential of these paths?
Wait, you want them to contain.
Yes, I want every union to contain your favorite bipartite graph.
The
Yes.
favorite bipartite graph should be in the union.
Yes, so each union you can find your favorite one somewhere, alright, you found it, that's fine. And what now?
And only exponential, not n factorial or something like that. Not n to the log n, but not n to the n.
Really?
So you require every union to have one instance of your favorite graph. Maybe for this union it's here, maybe for the other union it's somewhere else. I mean, in each union there should not be too many, of course, but so they could overlap and let's see why. So I don't see yet your argument, but maybe.
Let's go.
All right, so we can talk about it. Any more questions?
Okay, let us tell the speaker. I'm just